Okay, today we're gonna watch Bill Gaede go over Ether Through the Ages. He's gonna go live in a couple seconds. Now, but yeah, he should be going live any second now. So let me introduce you to Bill Gaede while we're still waiting for him. He's an engineer that he's on. He'll introduce himself.
That does physics at all. Okay, we're going to have a good time today. Okay, and I'm going to begin. Well, today we're going to be doing a little bit of ether, history of ether, and what you'll find out is that it parallels very closely, the history of gravity that we did last week. So if you look at that, ether was used as the medium for gravity, primarily for light. Okay, so all this really ties in together. And the interesting thing, what you're going to find out today, is that nothing has changed in the last 10,000 years. They are still using the ether, okay, to this the bit.
That is false. Things haven't changed in the last 1,000 years. So maybe we're still technically using the ether per his definition, but science has been progressing. Unlike what Bill Gaede has been saying, science has been progressing. We have been updating our models. Ironically, he really doesn't. He doesn't update his models much.
If there's something else, hey, if it's a thing, illustrate it. If it's a concept, define it. Very simple. Okay, but we're going to start with a little bit of language. There's a lot of people using four-letter words in science, and that's not allowed.
Like rope.
Okay? And so what am I talking about? Well, we're talking about this. These are all the four-letter words that people use in science. Okay, you use any of those, those are all unscientific terms, especially the first few there, energy, field, charge, wave, time, force. If you use any of those to make your case, to do your dissertation, to make your presentation, you are an irrational individual. You haven't gone through kindergarten physics. Okay? And so I'm going to be talking a little bit about the fact that a lot of people make their case using these words. And they don't understand that, and the context is the following, that they're using a concept as an object, as a thing.
What's
so
the
moving
difference?
The field, vibrating the energy, or transferring it, or lifting the mass. You can't do that in physics.
If an object's that would
first and foremost,
you imagine or that which has shape.
You need a thing.
What's the difference?
You can't do physics without things. If God wiped out all the things in the universe, left absolutely nothing, whatever nothing is, emptiness, space. If God did that, what's happening? What are you observing? What's taking place? And so you need things, and that's the first rule of physics. Okay,
we know you don't know what nothing
principle. You can't do physics without things. None of the words that you see there represent things. All of these are concepts, and when they're used as things, they are irrational. They're irrational concepts. Okay. So you can't use any of these words. They're outlawed. They're four-letter words as far as science, physics is concerned. Okay, and we're going to be talking a little bit about that today because we
says
individual who clarified what he clarified last week. He clarified it again. And what he doesn't understand is this, that he's using 4-letter words, okay? Outlawed in physics. Okay, but let me get to this first comment here. And fellow says, singularity, perfect, nothing. Okay, yeah, absolutely. Then he says, space, something, okay? Quantum wave. Well, for that, you need to define what space is and what wave is. Until we define those terms, we have no idea what you're talking about. Space is nothing, so it's not something, as you say there, okay? So if you believe strongly or you want to propose these terms, no problem, but you have to define them. That way we can follow your presentation. Okay, very simple. Okay, and so let's get to this fellow, and he had written a comment. I analyzed it, and then he came back the following week and said, let me clarify what I said, okay? And here, just very quickly, I'm just going to point to that center one, the one in green, the green box, electrodynamic forces between electrostatic fields. No, forces cannot be between fields. You can talk about horses being between two cornfields. Yeah, that you can talk about, but you cannot talk in physics about forces, concepts, right? Pull, push, being between two fields, whatever field is, okay? And so he said, let me clarify for you what I meant. Okay, let's go with the clarification.
Oh,
here we
this
go.
will be good.
And hello. So here we go. Fellow says, clarifying my clarifications. Okay, and electrodynamic forces between fields. Yeah, I wanted a clarification about that because I don't know what a force is. I don't know what a field is. Maybe he's talking about horses and between fields, cornfields. That I can understand. But forces between just fields, what kind of fields? Okay. And
No, you already defined
forces experienced by
charges on a field. You have field covered.
What is a charge?
You have field covered.
Fields.
You have a cornfield.
He's using this foul language, these 4-letter words that he's bringing in here. We don't know what a charge is. What is charge? What is a field? And he says charge is moving around them. How does a charge move? I mean, what are you talking about? Credit cards and he's charging? I don't know. I don't know what he's talking about. What is a charge? Okay. And again, all these words were put into his head, in his mouth, right? By the establishment, by the mathematicians out there who invented these words. Why? Because they could not explain. They could not explain a single phenomenon.
In a socket.
And so what they did was they created these concepts. And they fed them to us, all of us, including myself, in high school, in college, and so on. And so we just repeat and say, oh, the charge, oh, the field, oh, the energy. No such monsters in physics. And that's where the problem is. What they're doing is treating concepts as physical objects. This fellow doesn't understand that. And he talks about fields and charges and
wall sockets
and forces. And so, yeah, all I can do is ask him to define those words so that we can understand, we can follow his presentation, we can understand what he's saying. Okay, so that's the problem. That's the starting point. But he just went on and on, just rattling about a lot of stuff. And it's important to look at his language. I want you to look at his entire language. It says, how I think fields and electricity work. Okay, well, we'll find out what a field is, I guess, here. The water pressure analogy, where you have water going through a pipe, right, is not 100% accurate. Okay, it's better to think of waves moving. Waves do not move. Waves do not move because wave is already something in motion. It's like saying running runs or flying
in a
flies.
Wave pattern.
You can't swim, swim.
I agree. Waves don't move. The media moves.
Jumping. And that's what he said. Waves are moving. Waves are waving. Okay, waves travel.
No, water
waves are just electrons changing shape.
Particle.
Well, it's a changing shape.
It's a shape
in motion, anyways. Even if it's a changing shape, using the word changing means there's already motion embodied in the wave. So you can't say waves do this and waves do that because you cannot treat it as a noun. Wave.
Yeah, you say water
for the purposes of physics. In ordinary speech, you can say that.
Water does wave. Cars do wave.
In science, you cannot say that a wave does this and a wave does that because you're saying that running does this and jumping does that. Okay? And they absorb or emit photon. No, waves cannot absorb or emit anything. and much less photons, whatever those are. What are photons? I mean, are
Light.
those verbs as well?
Photons
I mean,
is
are we
light.
talking about a little ball, or are we talking about wave, which is already in motion, field, which is already in motion?
It's
You know,
like
so you need to tell us what a
look at it as a
photon
particle.
is.
That's
Are
what
we talking about a little,
photons is.
you know, stick, a little ball? What is a photon? Patterns of those shapes
Light.
changing. Okay, actions define the fields they produce. And again, you can't produce fields. Okay, because field is not a physical object. Field is a bunch of numbers. That's all it is. From ground zero, you know, you have all these values.
Can you
Whether
draw
you're talking about
a bunch of
gravitational
numbers?
field or electric field or
It's
magnetic
an
field, it
object.
doesn't matter.
By
What
your
you're talking
definition.
about is values becoming weaker as you get farther and farther away from ground zero. Okay, that's what you're talking about. And it just goes on and on. As he says, when you weigh yourself on a scale, you are pushing the scale, and the scale is pushing you. Okay, the ladder upwards, push being that what you experience as weight. Okay, you are pushing down on the scale because Earth and the scale is what? Gravitationally attracting you to it. Yeah. What do you mean by that? How? We need to know the mechanism. That's what we're interested in. That's what physics is about. But to say that gravity pulls on you, you haven't said anything because we're trying to figure out what gravity is. And the only way you're going to figure that out is by identifying the invisible, intangible mediators of gravity. Okay, whether this attraction is from ropes or some other mechanism, I guess, is irrelevant to your weight. Yeah, that's see, he thinks that's irrelevant. That's the only thing that is important. It's the other way around. Weight is a function of ropes in our model, and the more ropes you have, the more weight you have. How simple it is, because the closer you are to the object that's pulling you, for example, in this instance, the Earth. So yeah, it's the other way around. That is the only thing that's important.
How do we count
what you're going to say next is not important at all. Bill? Whether this attraction is from ropes or some mechanism is relevant.
How do we count them?
What matters is that you are in contact with a scale and you are being accelerated into it due to what? The gravity of something. The gravity of something. Yeah, that's what we want to know. We want to understand what is the gravity of, what is that something? That's the part of physics. And the rest is just nonsense. Okay. If you were free falling, the only thing that stopped you from completely weightless is that the atmosphere will slow you down. Yeah, you haven't said much. You know, we know all this. We know that a feather, if you let go of a feather, there's more resistance in the air than if you throw an elephant. No mystery there. So you haven't said anything. What we need to figure out is what's pulling it down or pushing it down. You know, if you like push gravity, no problem. Explain the mechanism. Yeah, it's the part that you omitted that is the important part. Okay, and you can't use those foul words, those four-letter words in your presentation. Okay, so here he says wires. Okay, all objects, including metallic wires, consist of atoms. Okay, what is an atom? And he says each atom contains positively charged protons. I don't know what a positively charged anything is. You know, I mean, charging your credit card, is that what you're saying? And an equal number of tiny negatively charged electrons. So I don't know what a positively charged or a negatively charged whatever is. But, you know, I illustrated what I think he's saying. He's saying there's a positive ball and a negative ball. Okay. Well, what's the problem with this? Here, I'll show you. It's his next statement. He says, orbiting around the core. Around the core. And what do you mean orbiting? You got to explain the mechanism. Why doesn't the electron bead, that electron that's got the negative sign, you know, carries a negative sign on its over its head, why doesn't it fly away? What's keeping it there? Why does it orbit? Why does it stay faithful to the proton? That's what you got to tell us. And the fellow tries to get away with what they, you know, taught him, what they learned him, you know, in school, in a monastery, I don't know. And that is that positive attracts negative. Okay, let's even go with that. If positive attracts negative, why doesn't the negative bead fall to the positive proton? I mean, that's what you got to explain. Why does it spontaneously fly away? Why does it fall towards the blue ball there? And he just says, no, it's just orbiting. It just stays there close to the proton, rolling around it.
Okay.
And so this is the
What's
problem.
your
The problem is that he just says things that he memorized, that they fed him, and he just repeats them. He regurgitates them like, it's self-evident and we know it all. No, we don't know nothing. I mean, that's not an atom. What you're talking about is an irrational atom, which is the planetary atom, because Bohr's model does not tell us why the electron bead doesn't fly away or fall to the nucleus.
Okay, I agree.
Okay, and then he goes into current. He says metals consist of a regular arrangement of densely packed atoms, okay, that have electrons that can freely move between the atoms. Why can they move between the atoms? What's pushing them?
Wait a second. Where are we supposed to be talking about?
How is it that the electron
electrons
abandons the atom? I mean, we have this.
What do electrons
ball,
do
which is the proton? We have the electron bead. What compels it to move out? Are you hitting it with something like a paddle, or what compels it to move? You just state that the electrons move, but that's based on the irrational planetary model. Okay, and so you got to start at the atom first and show us your atom and make it work before you say anything, before you explain anything. And of course, if you got this bead, you cannot explain your atom, let alone electricity, which is based on that model. Okay, so let's get that right. These properties make them good conductors of electricity. Okay, outer electrons in each atom are free to move within the metal lattice. Why? I mean, these are just statements. You got to tell us why. What's causing the electron to move? Is something pushing, something pulling? You got to tell us that. Conduction electrons conserved on charge carriers.
When you have
I don't know what a charge carrier is. As charge carriers, I mean, or carrying a current. How do you carry a current? I mean, you take a river over your shoulder and carry the river? Is that
that for sure?
I mean, it's all irrational language. That all of what comes out of his mouth is just irrational language.
We could skip
it's just words that he learned somewhere in the monastery, and he just regurgitates them. He says, "Oh, charge carriers." Like if you knew if he knew what he's talking about, let alone whoever listens.
We don't like them.
Metals are conductive because there are many free electrons. Well, they should put them in prison, I guess.
Prison?
Too many free electrons. That's the problem. Get it to your head.
Prison.
Okay, so here we have, he says, with no external electric field applied, okay, whatever that is, whatever a field is, right? These electrons move about randomly due to energy. We have field and energy, right? But there is zero current within the metal. Yeah, I assume there's no current. I mean, if there's no river, you have no current. I mean, what is he talking about? What is this field, this energy, this current? These four-letter words. The net force on each charge carrier is nearly zero because what? The field from other charges nearby cancel out. So the fields cancel out, whatever that is, whatever a field is. Okay, we're having a field day. The electrons are moving in circles.
We need to make a picture book.
You who's moving in circles like that dog.
Like he has his own picture book. Let me get it.
Okay? You're moving in circles. Okay, and he continues. He goes with this. He says that George Gamow wrote in his popular science book 1, 2, 3, Infinity, the metallic substances. See, this is where he gets his information. Differ from all other materials by the fact that the outer shells of their atoms are bound. What do you mean the outer shells? Where did the shell come in? All we had in the atom was a little ball and a big ball, a little red ball, negative sign on its hat, and the other positive on its cap in the center. How did we end up with this word shell? Where's the eggshell? I don't see any shell there. And then he continues, he says, rather loosely and often let one of their electrons go free. Yeah, again,
I'm showing Bill Gaede's picture book.
Prevents the little electron bead from falling towards the positive nucleus or leaving spontaneously the atom completely. And he continues, says, thus the interior, this is from him now, thus the interior of a metal is filled up with large number of what? Unattached electrons that travel aimlessly around like a crowd of displaced persons. I think it's you who are traveling aimlessly. What do you mean unattached electrons? They weren't attached to begin with. What were they attached with? That's what you got to tell us. And again, this fellow, he just uses words that he doesn't even know what he's saying. What do you mean attached? Attached to what? Is there a string attaching them?
To the proton. To the
I don't know what
proton.
he's talking about.
Attached to the proton.
And here he continues, says, when a middle wire is subjected to field pressure, I don't know, is he talking about a wheat field or maybe a football field? You know, you have these waves in the football field, you know? And so I don't know if there's some pressure there, you know, when you do the wave. Applied on its opposite ends voltage. Yeah, what is this voltage thingy? These free electrons rush in the direction of the field.
It's saying there's no field is.
The ball there in the middle of the field.
I mean,
what do you mean? Free electrons, what do you mean rushing towards the field? Field is a concept. You don't rush towards a concept. You don't rush towards love or, I don't know, grace.
It looks like an object.
Thus forming what we call an electric current. Yeah, I don't know what an electric current is. So you got to tell us what a current is. Current of what? Is it a river? You know, what is this current made of?
You draw it.
Made out of little balls, electron balls. Electron beads that are just flowing en masse away from their atoms. I mean, all this has to be visually. You have to tell us. You have to show us a picture, a movie. If you're going to talk about, you know, the flowing of what current. You know, I mean, if I tell you the current of a river, I can illustrate that. I can show you, look, there's a river, it's flowing. We call that a current. Everybody can understand that, okay? Even in ordinary speech, you may even understand it in physics, even though you can't use the word current as a thing, okay? But I can say, well, that's what we mean by current in ordinary speech, because you see all this water flowing. We call that water flowing a current. So what is flowing in the case of electricity? Is it all these electron beads? You know, why are they flowing? What's pulling them? What's pushing them? Why weren't they? Why didn't they leave
the power source
before you know, put the voltage there? All this stuff. What is this?
Power source
what
is the gravity analog.
The beads. Is it some paddle that hits them and they start moving? Is that how it works? I mean,
yes.
It's the mechanism that we're interested in.
The paddle's called a battery, Bill.
You know, the verbiage.
The paddle's called a battery. Or generator.
And,
so yes.
Well, he
yes, it is.
Here, a couple more here. It says motion of the charges. Motion of the charge. How can a charge move if a charge is 1 times 10 to the minus 19, 1.6 times 10 to the minus 19 coulombs? That's what a charge is. And he's saying the motion of this number. How can a number move? Coulomb. We're going to move the coulombs. It's still only the order of millimeters, I guess, because like charges repel each other. What do you mean like charges? You mean negative against negative? Why don't they add?
Double column count. It's not. It doesn't move.
Positive against positive, you get more positive.
At least
I mean, you know, it's this foul language that this poor fellow uses.
It's and debited.
And he continues there. The energy of the charges must be traveling. The energy must be traveling. Yeah, I guess. I mean, depends on how high you are.
Understand these
via waves of some sort.
And
again,
come on.
It just leaves that all up in the air, like it's some wave of some kind. I don't know, and I don't care. I just want to tell you my theory. You know, each wave impulse faster than the electrons. I mean, you know, waves can't impulse anything, right? Waves can be guided by current wires. No, by
that's why wave shape.
Wave is not a physical object.
Makes a wave shape.
Okay? And charge densities can act as a medium. Absolutely not. Charge is not a medium. Okay, and much less a density.
Look,
waves can cause field variations. Absolutely not. Waves is a concept.
It means my body.
Anything.
It makes a wave shape.
In field variation, which is a number in mathematics. They can escape the wires entirely. No, waves cannot escape, especially out of this universe. We call that radiation. What is radiation? You know, an escape wave, which can be in the form of heat.
In a wave stream.
Heat, radio, and light don't have form. Okay, not those words, at least.
It's self-traveling.
So yeah, this is the problem. They have. They're
look at your lights
with all this language.
That's radiation.
This is the language that they use. This
Look
is how
at
they
my
communicate their ideas.
Radiation. It starts bumping on my face.
This is what they learn, and they just
That's
regurgitate it
radiation.
without ever questioning
I think pretty simple.
instructors or teachers, whatever, priests. They never question them. Oh, what do you mean by wave? What do you mean by energy? What do you mean by field?
I asked what they mean, and
they
they
just say,
it's
I'm
pretty
going to use
simple
this
to
word.
me.
Nice word. And the problem
In
with
fact, you
that is that when
understand
you
most
come
we
here,
just play peekaboo.
and
Bill.
we don't
You play
use that foul
peekaboo.
language. We say, look, this is a horse, and this is a table, and this is a house, and this is a tree. And I think everybody can understand that because I point to them. I say, look, that's a tree, that's a house, that's a table, that's a chair, and so on. So you say, okay, I know what he's talking about. It's that thing that he pointed to. I put a name to the noun that I, pointed to, designated. So now I can say, I'm going to move the tree. Everybody can understand that because I can film it. I can, show you a movie of me moving the tree. And if I tell you that,
I can show a movie me turning on and off the light. Look,
here's the rock.
This is going to be the
Here's
movie.
flying,
Look.
and it broke the window.
Light off.
Do I need to know
Light
how
on.
thick the window is?
Light
No,
on.
I'm just wondering
Light
why
on.
the glass fell on the floor. Why it's all broken in pieces. I'm saying because the theory is that I threw a rock through the window. That's the mechanism. That's how the window broke. But these people say, look, there's a mass, and I threw it so much force, and the energy, hit the window and it broke. And we haven't understood squat because none of that is physics. None of that has anything to do with physics. And
you don't understand squat.
Follow
you don't understand squat.
Presentation using objects. You're talking kindergarten stuff here. Yeah, this is all physics is kindergarten. You don't need to know any math. You don't need to. You don't need to imagine beyond your wildest dreams. You just visualize or watch the movie, the mechanism. You say, okay, I understand how that happened. And that's the way we have to explain,
light on, Bill.
Why a spoon
falls
light on downwards. We have a spoon, and we have the earth. We know this.
Light off.
Our experiences,
light on.
Right?
Electricity.
That this always falls to the ground.
It's getting
all we
power
have to do is
from
explain it.
a source.
And for that, you're going to need some object.
The diode,
either pushing or pulling.
Radiates off my face.
There's no other, as far as I know, there's no other force, right? It's either push or pull. And so you have to identify the invisible mediators, intangible also, right? And once you do that, you can show the movie, and that's how easy gravity is. And the only reason that we're here, we are 10,000 years later, nobody can tell you what gravity is because no one has identified the invisible, intangible mediators. That's the whole issue. Once you identify them,
how does it mediate?
It's kindergarten. I mean, really kindergarten.
How can something intangible mediate anything?
Here's my model. I'm saying
tangibility is touch.
And I always show this. So I'm illustrating over this. It's not that I'm saying a rubber band is pulling, okay? But if I want to explain pull, very easy. I have a pen here. I put the
that's
rubber band,
rope,
right?
Bill.
And I pull it down.
Over an intangible rope.
See how easy it is? I can explain pull.
Not tangible
You
rope.
only if you see it without the rubber band, here I'll do it without the rubber band. You say, oh, how did that happen?
That's magic. Rope.
But if I show you the rubber band, you say, oh, okay, hey, that's so easy. That's kindergarten stuff,
Pull something with.
So the only difference between these is that you can see the mediator here, you cannot see it here. That's the only difference.
No, pull it.
That's what stumped all these researchers. They never realize that there are invisible, intangible mediators, and you're not going to elucidate, you're not going to imagine them or detect them in any way by going to the lab or going to the field and running some kind of experiment. You cannot determine these things or zero in on them through experiments. You cannot go to the lab. You cannot use your hands or your eyes. There's only one way, and that's
he's saying you can't figure out how to pull it intangible.
Then you can understand how this universe works. No problem. It's very easy.
You can't figure it out.
Father Universe and Mother Nature, they never went to school. They never learned math. All they know is they have to push one atom at a time everywhere in the universe. One atom from here to there, to there, and there to there. And all they do is just move one atom from one place to another throughout the universe. That's how easy it is. That's how easy our universe is. Okay, this fellow did have a good point here, and he said the following, and listen to this. It says, can you explain in detail how various components of a circuit work with ropes and threads?
Oh, this is gonna be great.
Yeah, the rope model.
This is
And
gonna be great.
I believe I've explained all of those. I cannot vouch completely, but I think I've explained all of them. And what I've done as a result of this request, I started with a battery today. Okay, about an hour ago, I uploaded a video.
Oh, this is my!
2018.
This is
what I did,
hilarious.
I chopped it up, edited
It's like he
it,
doesn't remember what
and
you
I
said.
started with the battery. And I'll be going through these in that channel.
He
That,
said earlier in this presentation he didn't understand
series of videos.
the freaking circuits.
Through all the things involved in
saying,
electricity. So all these things I'll be
touching electrons
upon. I'll just go through my videos and find out which ones I've already covered. And if I haven't covered one, then I will cover it. So I started with battery, and I'll be uploading some of these videos in the coming weeks. Okay. So I will answer his question. I thought it was a good idea to do it anyways, because I've done some of these in the past, and people may wonder, how do you do electricity with the rope model? How do you do light? How do you do gravity? And so it's a fair question, especially for electricity. So I'm going to do just electricity in that channel. Okay, so here we have the problem that I'll have with this gentleman, because he hasn't gone through kindergarten physics. He hasn't learned the scientific method. Okay, he doesn't know what the scientific method is, because
Bill Gaede has a proprietary scientific method.
Objects were nouns, were things for the purposes of physics. And so we have to start here, and this is where he's got to start. He's got to go to kindergarten. Okay, what is science? Rational explanations. In science, we do not describe. In science, we explain. And we're not interested in philosophy in this channel, not very much at least.
I don't know anyone else that uses
physics. Well, first of all, you have to have an object.
Super
you have to have
special,
a thing.
Awesome.
Yeah, without a thing,
I don't know anyone else.
Nothing. So nothing is happening. Okay, that's the first one. Then what do? We explain causes and mechanisms. And there on the right-hand side, we show the rational scientific method as applied to physics. And we have what is known as the hypothesis, which is not a theory, which is not an explanation. It's not a tentative theory or anything that it means in the real.
Yeah, I had electricity spinning electron being queued up. He did explain this before. So basically, he has electrons and gets functioning as balls of yarn, spinning, and just shells of some kind. And the phantom threads come out and knock each other around, even though they're invisible and intangible, which makes no sense. Let's continue.
And then causes, that's the theory, and finally the conclusions. So this fellow has to go through this. He has never seen this, I guess. He's never been to kindergarten physics. He just jumps ahead and say, because a lot of these people, they go to the labs and they know how to handle a resistor, or they deal with voltmeters, and they measure current, and they work with all this stuff. They know it like the palm of their hands, but they never understand what's happening at the atomic and subatomic levels. That's where they fail. They have no idea what's going on with carriers and, as they're known, atoms, electrons. They don't know what's going on in that invisible world. They never visualize it. They just say, hey, I know that if I put my two electrodes here, I measure so much current, so much resistance, so much voltage. That they know by heart. They know how to handle an oscilloscope, voltmeter. They all that stuff they know. They're usually electricians, a lot of these folks, but they know nothing about physics, because physics is none of that.
Bill Gaede is
physics is about explaining the mechanism, especially at the atomic and subatomic.
He doesn't say anyone other than him knows anything about
mediator, what the mediator of light is, what the mediator of this so-called
field he's the only physicist in
what
the
is a field
universe.
You have to tell us when you transfer energy, what it is that you transferred. You need to see the picture of that thing that you call energy, and so on down the line. And they're not used to doing that, and that's when they come here and you say, hey, what does the ether look like? Please illustrate it for me. Why are you asking that question? What kind of question is that? What do you mean? What does the ether look like? Or what is the ether? Let me tell you my theory. So they skip over the important part, illustrating or defining the ether. And they never do that. They never learn that. That's the first step. And so they jump
the ether
past the first step and they want to tell you their theory. They say, let me tell you how this universe works. How can you tell me how this universe works if you don't know what the ether is? And ether is the foundation of your theory. So yeah, the first step is you got to point to the ether.
Okay, point to the ether.
And so we're going to do that in a minute here. We're going to go into what the ether is, or the history of the ether. Okay.
Yeah, we're half hour in.
So let's move on. Oh, well, I had one more issue here.
Half hour in.
Let me show you this. So it says, as long as God was a bush or a magician, it was okay for a starting point. Okay. But when we try to explain his actions, also known as miracles, then we run into problems. No kidding. Like making nothing morph into something in zero time. Right there, you see it. First frame in the film, the one on the left, far left.
Nothing doesn't have to morph into something.
We'll put black,
nothing.
and we'll call that nothing, right? There's nothing there. And suddenly in frame number one, or number two, let's call it number two, we see a little dot. And that could be a singularity, it can be whatever you want it to be, it doesn't matter. Suddenly we went from nothing to something. And God did it in zero time because it's the next frame in the film. And you can chop the film as much as you want, no matter how much you want.
Nothing and something to see.
It doesn't matter. The next frame in the film, you already have something. How did God do it? The mechanism. That's what we want to see. And of course, when they talk about singularities, mathematical physicists, they go in there and they say, look, we can't tell you what happened in frame number one. We start at frame number two. Yeah, no kidding. And yeah, he says, how does it happen? Can that be rationally explained? Absolutely not. Right? Not even God can explain that. Okay. And yeah, then, from there we have the universe, right? And so, yes, this is the problem. The problem is that you need to define the language and you need to show us the pictures of the objects that underlie your theory.
Okay, we're going to look at the ether.
You cannot do that. You are not a scientist.
Okay, show us the ether.
Okay, let's move on to our main course for the day, and that is the ether. I'm going to talk a little bit about the history of the ether. Where did this ether come from, and why have we never gotten rid of it?
40 minutes in,
we
just got to talk.
Right? Okay. The ether probably preceded these two fellows. Okay, but they are credited with really discussing the ether to some degree early on, to analyzing and that kind of thing, And so we have Plato on the left and Aristotle on the right, the two Greek guys. And so how did they visualize the ether? Well, I cannot tell you exactly that this is the way they saw it, but they really thought that the ether pervaded everything, in the universe, except that maybe this is not completely correct, because the way they looked at it is the ether was not here on Earth. It was out there, like giving kind of a background to the universe.
Well, that's saying non-object according to your definition, Bill.
So if you look at
it's not an object, so I guess you didn't show us the ether.
Later after
you're not a scientist.
And he devised this world in which the Earth was really at the center. The sun was rolling around the Earth, right?
We have two objects.
And what happened? Well, the ether was outside
two objects of
at least our solar system, if not outside our universe. So he saw it as all these particles like air that was what the gods breathed. Okay, so it was what they breathed, not what we breathe. We breathe air; they breathe ether, and the ether was obviously responsible for all that stuff that we could not explain. And in such a way, they, essentially put it way past anybody's ability to visualize it. It sits out there, don't bother me. It was more or less like that. Okay, so where did we go from there? Well, what it was used for primarily was for this. here you have the flat Earth model. Okay, you have the sun rolling around flat Earth. A lot of people believed in that for some time. But even when with a flat model, right, a flat Earth model, they had this
Pancake
ether in the
planet.
background. You know, they always thought it was the ether that somehow had something to do with the sun, with the movement of stars, etc. Not so much the stars because they were too far away and they thought they were still, but yeah, with everything that they could see moving in our solar system, like the planets and so on. Well, from this, some of the more enlightened people out there, they figured out the what is known today as the Ptolemaic system of epicycles. It looks more or less like this. Okay, so you had all these planets, and including the sun, moving around the Earth. Okay, but again, this model also had the ether in the background. Okay, so this is the way they visualize. They say, yeah, what's moving all this stuff is the ether, or this stuff is moving through the ether. Okay, so they had no problem with imagining it like that, and they just left it at that because they said, we'll never figure it out. And we're still there today, right? A lot of these people say, we'll never figure it out, how this universe works, even though, like I said, it's kindergarten stuff. Okay, and so here's the model that came afterwards, the one from Kepler and Tycho Brahe and other people, astronomers / astrologers. They did a little bit of everything. But even their model, consisted of this ether model where the ether was in the background. Okay, so this is how they imagined it, because the ether had not gone away. And the ether was all these bunch of particles that were in the background.
Okay.
That's the way they visualized or imagined it. They didn't know what the ether was, but they said there's got to be something there. And then the only issue that really came up with all these people were the properties of the ether. So they started pondering, what kind of properties does this medium have? Is it an ocean of what? And so they imagined it as particles. Okay, and the only thing that came to their mind, all these loose particles. And you have someone like Descartes, René Descartes, and he was a big man in his days. He was well respected for many years, even after his death. And so he was like, the Einstein of his age, so to speak. And he had these little spirals, these vortices, okay?
Yes.
And that's what he proposed the ether was. He had this particle notion, but he had them swirling around in these spirals, right? And so René said the following. He says, there is no such thing as a void or vacuum. He didn't believe in space, just like Aristotle did not believe that there was such a thing as empty space. He just said when something moves, something else takes its place. And the question is, how can it move if it doesn't have space to move into? And they said, well, it just replaces another object. And so he equates the ether with space. Okay, this medium fills space completely except for tiny separations between the vortices. Yeah, and he downplayed that, but that's an extremely important part of his fake hypothesis, because
how do you separate the
vortex from another?
That's
what's between the vortices. And it never occurred to him that if there's a separation, something has to be separating those two vortices. And it just never clicked on him. Now he visualizes it like an ocean, right? The disturbance we call light is a statical pressure in this medium. I like that statical pressure. I thought pressure was movement, but he's got a static one, right? And so ether is the medium of light. So they had
pressure is the average of movement
vibrating somehow. In his case, it was
a summary of the movement,
and that was light.
Light was just a summary of all the movement.
And he says vortices in this ether are responsible for the accumulation of the particles that form matter and shape solid objects. So the objects themselves are eventually made of ether itself, right?
Yes.
He postulates a vortex of fluid matter,
it's a summary.
And matter of the vortex enters one pole and leaves the other. Okay, how that produces attraction or repulsion, we don't know, but that's how he imagined it. Okay, and this is how he made his presentation. And he was considered, like I said, a big man. He was the Einstein of his age. He was well respected by a lot of these folks. A few years later, we have this other fellow. His name is Robert Boyle, and he studied vacuum. Charles II would say that, I'm paying all this money, and this guy is studying what? Air? because he was very fond of vacuum, vacuum chambers, right? So he worked a lot with that. And he was also head of the Royal Society. In fact, he was really the main man who created it. And he says the ether also, he believed in the ether, a diffused and very subtle substance consisting of what? Subtle particles. There you have it, folks. Subtle particles. There's always in the air a swarm of streams moving in a determinate course between the North Pole and the South Pole. Okay, so he had these particles flowing essentially, from one region of the earth to the other. That was his notion. But in between, we had these other fellows. This fellow, his name was Robert Hooke, and he was really the lab boy for Boyle. Okay, and Hooke was a fellow that really investigated the ether and wrote about it quite a bit. One of the first to write about it. And again, the reason you see a question mark there is that Newton hated Hooke's guts. And when Newton took over the Royal Society after Hooke's death, he destroyed everything that Hooke made. In fact, even his pictures. So we don't have a picture of Robert Hooke today. You'll find pictures on the internet, but they don't know if that's him. And more than likely, it's not. Newton made sure that nobody ever saw Robert Hooke again. And this is what Hooke said. He said, light is not propagated through air in straight lines. He said it's undulate. He's the guy who discovers the wave nature of light. Really, he's the guy who really starts with that. He said there is some illumination within the geometrical shadow of an opaque body. He had this notion of diffraction. That came from Grimaldi, not from him, but he picked up on that, right? So he said, the only way we can explain that is with waves. So he's really the wave guy, but he was thinking of longitudinal waves, right? And he continues, he says, discovers the wave nature of light, okay? Transitional from Descartes' system of vortices to a fully developed theory of undulations. So he did not agree, in fact, with Descartes because Robert Hooke did not believe that light had a mediator, that there was a medium for light. He said it's the same ether that is vibrating. That is, which is everywhere, but when it vibrates locally, that's what we call light. Okay? He attacks Descartes' theory that light is a tendency to motion rather than actual motion. And he specified there is no luminous body. Okay, and listen to that. He says there is no body, but has the parts of it in motion, meaning the ether. He's saying the ether is what is moving. There is no.
Yeah, no wonder people try not to do live response videos. There's a whole bunch of fluff I can edit this down with. If only I knew how to use Blender properly. This is fluff I don't need to. I mean, I may get a timestamp people can skip to the next good part.
Any mass? Well, it's not getting rid of anything which is material. That was his notion. That was his reasoning. Ether motion must be of a vibratory character, meaning waves, right? And Hooke charged Newton with holding the doctrine that light is a material substance. And Newton later on denied that he wasn't willing to stick his neck out because he said, look, I'm not interested in all that stuff. But Hooke really accused him of that. One of the reasons they argued a lot and fought a lot, okay? And but anyways, Hooke continues with the ether. Now he's going to give you some properties of the ether. He says, ether must be a transparent, homogeneous body.
I disagree myself. This is not fluff.
Body susceptible to and capable of imparting motion. Okay, so the ether is not only malleable, but it can impart motion. Okay, both. The constitution and motion of the parts must be such that a pulse of the luminous body may be communicated or propagated through it to the greatest imaginable distance, right? Because light was so fast, right? In the least imaginable time, although not in an instant. Okay, so he's talking about the properties of the ether. That's his ether, right? Motion is propagated in every direction through this homogeneous medium with equal velocity by direct or straight rays extending radially from the center of a sphere. hey, there's our model. You have all these rays coming out of a sphere, right? The atom, it's got all these threads sticking outwards in every direction of the universe. So he more or less figured that one out, but he didn't come up with our model of our atom, right? Every pulse or vibration of the luminous body will generate an expanding sphere like waves or rings on the surface of the water. Okay, so this was his notion. And again, he's the first person really to propose the wave nature of light. He had a microscope, he was looking there, he saw rings.
Yeah, the medium waves.
That's not particles, that's waves.
Okay? Yeah, the water waves.
Looks like
my hand waves.
Stone in the water and having all these ripples move away from ground zero. That's more or less what he visualized light as. And of course, then came his nemesis, Mr. Newton, and he said all space is permeated by an elastic medium or ether. So they all believed in the ether. Every single one in the 17th century, they all thought there was this ether, this ocean out there. And that's what they charged with being the medium that created light, gravity, and who knows what else, which is capable of propagating vibrations in the same way as the air propagates the vibration of sound, but with far greater velocity, okay? This ether pervades the pores of all material bodies. So far, they're all pretty much, on the same page, right? Ether causes the cohesion of material bodies. Ether density varies from one body to another, being greatest in the free interplanetary spaces, okay? So he says there's a lot of ether between us and the moon. It is not necessarily a single uniform substance. Air contains water vapor, hence the ether may contain what? Ethereal spirits. So we have spirits out there. We're introducing the soul and who knows what, the angels. Produces phenomena such as electricity, magnetism, and gravitation. Light does not consist of vibrations of the ether, quite unlike Hooke. You can see there he criticized Hooke for that. And remember, Newton was the newcomer, so Hooke was saying, well, who's this kid who tells me that it's not the vibration of the ether? And that's when they began their fighting. And he says, light is something of a different kind that lucid bodies propagate. Okay, so Newton was the idea that light did have a mediator, whereas Hooke did not. Hooke said it's the vibration of the ether. And that's going to be the fight for the next couple centuries. Is there a mediator for light or is there not? And some people say, yeah, it's the ether itself, which is everything in the universe because it's just a bunch of particles and it's vibrating here. And we call that little vibration there the light or whatever you want to call it. And the other said, no, there's something that's moving through the ether. So those were the two general notions that we have out there for like 2 or 3 centuries, at least since the 17th century. And here he continues that some etherists suppose, this is interesting because it shows that Newton didn't give a damn about all this stuff. He wanted to describe it mathematically. He did not want to explain it or give you causes or mechanisms. So he says some etherists suppose the ether to consist of an aggregate of various peripatetic qualities. Other theorists suppose it to be comprised of unimaginably small corpuscles of various sizes. Ether initially accelerates these particles until the resistance of the ethereal medium equals the force of that accelerated them. Much like bodies that fall in water are accelerated until the resistance of the water equals the force of gravity. Okay, so you can see what he's talking about there. He's saying you throw, your lifesaver into the water, it doesn't sink. It's pushed up by the water. And that's more or less what he was saying. But here's the interesting part from Newton. It says, to avoid dispute and make the hypothesis general, let every man here take his fancy. Just, think whatever you want. Only whatever light be, I suppose it consists of rays differing from one another in contingent circumstances, as bigness, form, or vigor. In any case, light and ether are capable of mutual interaction. So he's saying light is something different than the ether. That's the first thing. And then they obviously there must be something because they can interact, right? Ether is in fact the intermediary between light and ponderable matter. And so he's saying light is something, and that's what Hooke was criticizing. And so we have a difference here. Either the ether is light is the vibration of the ether, or there's something moving through the ether separate from the ether, which we call light. And Newton favored the latter. He championed the latter. Okay, for the 17th century, we can just put a couple more here real quick. One is Torricelli, who said light is transmitted as readily through a vacuum as through air. He did not know that there was a refractive index. At the time, it seemed to him that it all had the same speed through any medium, right? Which it does, by the way. Light always travels at 300,000 kilometers per second under the Roche model, okay? It's refracted and diffracted. It just moves from atom to atom along the ropes. So there is no difference in speed of light. It always travels at the same speed. I can't say everywhere in the universe because I don't know what's out there on the edges of the universe. But for the main part of the universe, I would say light travels always at the same speed. And then here you have Huygens, and he says the medium of ether, he picks up on Torricelli's comment, right? And he says the medium of ether in which propagation takes place must penetrate all matter and be present even in all so-called vacua. So he did not believe, Huygens, that
vacuum means vacuums.
There's any space without ether. Okay, and again, the problem that all these people had is that when you say that, what is the ether? If it's a bunch of particles as they all imagined them, what separates one particle from the other? What is there between two particles of ether? You know, the ether is the whole
magic
ocean,
rope and phantom thread,
and it's made out of all these particles. Something must separate one particle from the other. You got to identify that something. If they're round, you got even bigger problem. I mean, if they're cubic, no problem because, or not as much problem because at least one block is next to the other block. But if they're separated, something is between them separating them. Otherwise, it'd be a single block. You know, the block universe, the real block universe. But if they're separated and if they're roundish, well, then you're in big trouble because now you have these interstices, and you got to explain to us. You know, what is that stuff there? Empty space? No, I thought you said space did not exist. So this is the problem. This is where they really screwed up badly. Okay, so that was the 17th century. Took a couple more centuries for these people to get their act more or less together. And the first guy to come up really at the very beginning of the 19th century, 1801 to 1803, we hates Newton, but because he says, look, you know, I think Newton was not really correct. And he was trying to criticize, you know, Newton, who was this big name out there. So he had to be very careful. And he goes out there and he says, look, you know, I believe in that light is really a wave of some kind, you know, that of some kind. He could not imagine what it could be, you know, but he says it's some kind of wave because look, I do the slit experiment and I get this interference pattern. And he says that can only be explained with waves. You cannot explain this with light, with particles. If it were corpuscles, as Newton called them, right, you would have only two lines on the screen, you know, which are the two lines in the slit, okay, in the double slit. And so he said, no, this has to be some kind of interference pattern produced by waves. And this changes the ball game because now everybody in the 19th century, right, begins talking about waves. And what is it that's waving? Again, we have the ether. But what is it that's waving? Is it the ether? Is it something that's going through the ether? And people wanted to think it was the ether itself, but they never really put their finger on what is the ether. Because if ether is the medium, whether it's, you know, if it's vibrating, it's undulating, it's waving, then the medium is ether. So you do have to identify. You have to tell me what the ether is if you're going to wave it. You know, I mean, if I wave a flag, right? I have to have the flag. I can't say, look, I'm waving and the flag. And you say, well, where's the flag? I forgot it. No, here's the flag. You got to show the flag and then you can wave it. And they don't do that with the ether. They say it's the waving of the ether. And of course, everybody in the back of their mind
just
said
say the background
a bunch of particles, but nobody specified that specifically. Nobody really
easy to work around. Just say the background treat is a solid object.
Identify the objects in physics,
so we can move through it.
And what happened was this: in 1818, there was a little contest in France. Okay, and the issue came around because they wanted to explain
like ghosts. Yeah,
the wave nature of light.
That's
the guy who appears is Fresnel. And he comes in there and he says, look, I can explain it. And he has this picket fence mechanism where he says, look, looks like light has to be a transverse wave. It's not a longitudinal wave as Huygens and Hooke and all these other people thought. No, it's a transverse wave, and that changes everything because he says, look, what you have here is like a picket fence. The picket is standing up and down, right? And you send the wave, the transverse wave. What the picket fence does is eliminate or prevent the horizontal component of the transverse wave. It stops that and allows only the other one to go through. And with that, he was able to explain some things, and a lot of people liked it, except one guy, and his name was Poisson. Okay, and there you have the picket fence mechanism that Fresnel proposed. Poisson, he comes in there, he says, look, you're full of it. He was a very guy who, a great fan of Newton's. And so he said, no, a light is a bunch of particles. And so Poisson just speculates, he theorizes that if Fresnel is right, if he's correct, I can prove that he's going to die. He's wrong. And I'll tell you why. Because if he's correct, there should be a little dot, little bright spot in the center of, if you have an obstacle there, the light should be able to go around that and converge upon that point, around the obstacle and converge upon a point. We should see a little bright dot. And it turns out he wanted to destroy Fresnel's theory by using this thought experiment. It turns out that Francois Arago, he goes in there, he does the experiment, and that's why it should be called maybe the Arago spot instead of the Poisson spot, and some people do call it the Arago spot. And he showed that indeed there was a dot in the center right behind the obstacle. And so he gave the prize to Fresnel and said, hey, this guy won because he really showed that light does have wave characteristics. It turns out that later on, when he looked up the history books, he found out that this other guy, the Lille, he had already proven that the spot like almost 100 years earlier. And so it should be called the Lille spot. And I'm not sure which of these names is easier to pronounce.
Interesting.
So
that's interesting.
The issue was that they had this wave nature, and then the
scientific drag gets awarded.
Was grounded in stone for the rest of the 19th century until the end of the century, obviously. And so, what were they talking about? They said, well, it's this luminiferous ether, okay, and light is just a vibration of that ether. They had this ether just flowing through the solar system in this example, right? And so they said, well, how can we prove the existence of the ether? Again, they were trying to say that there's something out there, and that's what light is. Okay, we've proven it through the slit experiment. We know it's a wave. We know the Poisson spot exists, etc. So how do we show that it's out there in the solar system, that we have all this ether flowing through us? And so they had this notion, as you can see, it's made out of a bunch of particles, right? And they're all moving across the solar system. That's what the arrows indicate at the bottom. So this was their notion. Okay? This is what everybody thought the ether was, and really nothing had changed. Or we can say something has changed. Some of them saw the ether as something static, what I call a sandbox. The Earth was moving through the sandbox. And everything was still, and the only thing moving were the planets and everything else through a sandbox. And that didn't work very well. So people say, no, it's dynamic. It sometimes moves, sometimes it doesn't. And so they started looking at the properties of the ether. And one fellow, his name is George Stokes, and he was head of the Royal Society, so he pulled his weight, right? And he came with the entrainment theory. And I like how he cheats. He says the ether is a fluid at slow speeds and rigid at fast speeds. He wanted to cover all the bases. He says, I need both. Thus, the Earth can move through the ether fairly freely because it's a fluid, but ether would be rigid enough to support light. Because in order to do light, they said, in order to have a standing wave or a transverse wave, you need to have a rigid medium, rigid mediator. So, well, is the ether fluid or is it rigid? And so here, let me show you something here. If I have a string, I want to run a standing wave, see if I can do this right, something like that. Well, anyways, what's the problem? Well, they said this has to be rigid in order to do that. But I'm saying more than rigid, you need something else. And that never crossed their minds. And that is, you need to have it tied at the other end.
Oh, okay.
You know, try to do this with your clothesline, right? If you don't tie it at the other end, this is what you get. You get an old man's, well, you know. So you need to have it tied at the other end. They never figure this out, that you need this. You need to have it tied at the other end. They said, we need it rigid. You need something more than that. You need to tie it at the other end. Otherwise, you can't do this. So you can only run a standing wave or a transverse wave, not if you send it in one way, you know, like a bunch of particles or who knows what a wave is. No, if you want to send it forward, you need to have it attached. The mediator has to be attached at the other end.
No, no,
and they never realized this. Okay? That everything, every atom in the universe has to be connected. There's no other way. Okay, here we have Max, good old Max. And what did Maxwell say? Well, he was a guy who said, hey, you need a mediator. And Newton was also a guy who said you need a mediator for gravity or light, but he didn't know what it was. Simulated it with particles. And you can't explain light or gravity with one-way particles. And so here's little Max. He said, there appears to be in the minds of these eminent men some prejudice or a priori objection against the hypothesis of a medium in which electric action at a distance take place. The existence of a medium in which light is propagated. He says there's prejudice. They were against it, many of these people. Whenever energy is transmitted from one body to another in time, energy transmitted, how do you transmit energy? There must be a medium. Nobody ever realized that you need a medium. You need a thing. You need an object. And nobody ever realized this. That's what's incredible. Or substance in which the energy exists after it leaves one body before it reaches the other. Absolutely. You need a mediator. I don't care if you put a string, but you need a mediator between two objects. Two atoms in this case. So James Maxwell at least realized that, but he couldn't figure out what it was because he was thinking of see and touch.
Between one object.
Says, I can't see this mediator, I can't touch it, but there has to be one, otherwise we're all crazy. And he did not understand what he was saying was coming out of his mouth. Yes, you need a mediator. And to this day, we have no mediator. They have concepts in mathematical physics. They do everything with concepts. Electric universe does the same thing. Etherists do the same thing. They want to do it all with concepts. Now you need a physical object. You need a dog. You need a couch. You need a tree. You need a dog. You need a chain. You need some kind of object. You can't do it with field and energy and mass and time. You can't use concepts as mediators, which is what they do. They say, oh, we bent time and I transferred the energy and, the field is vibrating. You can't talk like that in physics. That's irrational physics. Okay, and so this is what they came up with, the transverse wave. Good old Max came up with this. And you can see why they confused the rope with that, because they thought it was waves moving from A to B, and nothing was really moving. It's a rope torquing in place. And you can see
magic rope.
It's got a wave. It's already got a wave nature. All you have to do is twirl it, and then you have the wave, the torsion wave, not a transverse wave. And obviously, torsion wave, if we're going to talk about waves, torsion wave is much, much faster. I mean, infinitely times faster than the transverse wave or a longitudinal wave for that matter.
No, so that's math.
Torsion wave beats anything. It's the fastest thing that you can imagine because it doesn't go anywhere. So the signal travel. I mean, you can try this at home. Just go to your clothesline, twist it a little bit with a couple of clothespins at each end, and the other one moves instantaneously, essentially. Okay, and there you can see why velocity of light is equal to frequency times wavelength. We're talking about lengths of the rope. The more lengths you have per meter unit length, right? The more you have, the more lengths you have per unit length, the smaller, the shorter the lengths are, and vice versa. So it's very straightforward. And that's why, the velocity of light is always a constant. That's why c is always 300,000 kilometers per second. It better not change, otherwise we're all crazy. Okay, here we have a little later, we have good old Lorentz. And his equation really existed, the V over C that they use squared, right? That already came around. He didn't come up with that. That was already there before him, but he used it to prove that when you move through the ether, right, length contracts. Einstein did not come up with that. Einstein was still in shorts. He was a kid when Lorentz came up with that. And here you see he's saying there's a stationary medium made of countless particles, obviously, right, known as the ether, okay, a stationary medium. The Earth moves through this sandbox, right? Electromagnetic waves also travel through the medium. Speed of light, little c, is constant in all directions, and objects contract and time dilates as they move through the ether. How did he come up with all that nonsense? Well, there you see the Lorentz factor, as it's called, that gamma. And the crucial part is the v squared over c squared. V squared being the velocity of the object. The closer it approaches the speed of light, the more that approaches 1 v over c. I mean, if those two numbers are exactly the same, 300,000 kilometers per second, then you have 1. You have 1 minus 1, that's 0. Square root of 0 is, guess what? It's 0. And 1 over 0 is what? Well, you figure it out. So that's how he comes up with this notion that there is an ether, because he was trying to explain the results of the Michelson-Morley experiment. That's experiments with us, right? They did a couple of these. And they said, look, there is no ether. And so he said, no, there has to be an ether. What do you mean there's no ether? And so let me prove to you that there's an ether. He said, I know why you didn't notice any change, because your apparatus, your equipment shrunk. It shrunk in the direction of motion. Okay, and that's how they came up with that V. That's why V over C, that little.
I missed the joke.
Factor is.
I don't understand the joke
in mathematical physics. Okay, so and Einstein picked up on that.
I don't understand the funny
Einstein
part.
had a different notion of the ether. He did have an ether. In fact, he wrote a book about it. There you see it, the ether, the Relativitätstheorie. Okay, and he said the following. He says, we may say that according to the general theory of relativity, space is endowed with physical qualities. Okay, space has physical qualities. It's not nothing, it is something. In this sense, therefore, there exists an ether. According to the general theory of relativity, space without ether is unthinkable. And he gave that lecture over there in 1920 at the University of Leiden. And he believed in the ether, but he had a different notion of the ether than Lorentz. And the only difference was that in the case of Lorentz, he used the ether as a reference, whereas Einstein said, look, in relativity, everything is relative. There is no reference point. You can't put a stake and say, I'm going to measure my distance with respect to that. Okay, and so that's where they differ. But the ether was the ether was the ether. The ether never changed. One just said, look, it's static. The other guy said it's dynamic. This one says you can't use it as a reference. The other one says you can. The other guy said, I'm going to give it properties of both worlds. I'm going to cover all the bases. I'm going to make sure it's rigid and it's also malleable. And they had all these contradictions because they couldn't figure out what light or gravity are. That's where the problem was. So where are we today with the ether? Well, here we'll have a Nobel Prize tell us. Okay, here's the Nobel Prize. If he can't tell you, nobody can. Okay, here it is. And that's Robert Lofton. He says, the modern concept of the vacuum of space, confirmed every day by experiment, is a relativistic what? Ether.
Ether.
I said the word, 4-letter word. Okay, relativistic ether. But we do not call it this because it is
5 letters.
taboo. Okay, so please don't call it the ether because you're going to offend all the etherists that belong in the, in mathematical physics. They all believe in the ether. They've always had it. And here, in fact, let's illustrate it. What the hell? Let's illustrate. Here's the ether for you, folks. Ether from quantum, and it's the same thing for relativity. Relativity, remember, relativity holds that space-time. What is the definition of space-time?
Figure out which ether they believe in.
The aggregate of events. What's an event? A point in space-time. So if you take all these points, all these happenings, all these occurrences, that is space-time. And it's just a point here and there. So you're having, what are those points? Particles. That's what they mean by that. But they don't call it particle because that's taboo as well. You can't call it the ether. But here it is, folks. There you have it. You have all these particles coming in from the void, from the dark energy out there, I guess, and it's popping in and out of existence constantly. That's the ether of today. It's a little different than the more rational ether that these other people had, in the sense that they said, look, it's a sandbox. The other guy says, no, it's an ocean. These guys say, no, it's even worse than that. The particles are appearing from nowhere. We have God in there, making each one of these little particles come in from nowhere. Or maybe it's like this. I mean, this is another possibility. Here it is. Oh, no. Oh, it's the same one. Okay. Not the one I wanted to show. Anyways, here's the ether of the old days. Okay. That was the ether of the old days. Let's put it here. Let me get this one.
Live demos.
So there you see the two ethers. The ether on the lower right, that's one we've had all these hundreds of years. And the ether now is that they appear out of the void from nowhere. Okay. And so you take your pick, which ether you want. And what can we say? This is the ether we have.
What difference does it make?
After 10,000 years of dealing with the ether. Really numbing. That all these hundreds of years, thousands of years, they've had this ether, which is just a bunch of particles, and they've just given it different properties. That's all they've done with the ether. And if you have a bunch of particles, that's not a thing. That's not an object. You cannot call that an object, because the table is also a bunch of particles, and so is an elephant. So is a tree, a rock. They're all a bunch of particles. They're all atoms. So what we're going to say, what is a rock? A rock is a bunch of particles. And what is a table? A bunch of particles. And a chair is a bunch of particles. My dog is a bunch of particles. No, then you cannot say that the ether is a bunch of particles and that is an object.
Oh, okay.
You can't use it like that. You got to point to it, completely, and it has to have a shape. Then you can say that's the ether. Then I can point to it. But if you make it infinite, there's no object that is infinite. Okay, so you better enclose it with something and tell us what's enclosing it, also giving it a shape. So again, the ether is a problem, because if it is a bunch of particles, you got to tell me what the black stuff between the particles is. What separates one particle from the other? And to this day, they have never figured that out, because what stumped them is the fact that they could not see or touch whatever this ether thingy is. And that's where we stand today. We'll see you next Sunday.
Okay. Let's go. The electricity one's not that long. Let's start watching that one too.
We're trying to explain how we store motion.
Oh, this was another
I like to talk about motion, because when we say, well, store energy, everybody says, oh, I know what he's talking about. And
this was just an added down.
So it's better to say store motion, and that kind of jerks your ear. You say, what do you mean store motion? Yeah, that's what we're going to talk about. How you store motion so that you can deliver it or relay it later on to something else. And that's essentially what a battery does. And one of the issues that I found as I do my research on this subject is that there's a great misunderstanding out there in the regular world. If you look at a lot of the videos that are shown, like on YouTube and so on, they'll show that like a cable, and shows the electrons moving along the cable. They're all moving in a straight line. And I think this is the first myth that has to be at least clarified, because people forget that that's not what really happens. What happens is something else. And what happens is that, the electrons are circling in that wire. They're spiraling. And here, let me show you first.
Okay, more screen space.
Figure I have there. You can see that according to Fleming's left-hand rule, an electron which is within a magnetic field will go in circles. In fact, that's the explanation I give for black holes. I'm saying that's exactly what's happening when a star circles around nothing. It's not that there's a black hole in the center. It's that it's circling because it's in a magnetic field. All
Oh,
stars,
oh,
pretty
now,
much, they all have their own magnetic field. But here you see,
oh, okay. So past Bill Gaede, has no problem using electromagnetic fields. He has no problem with fields. He knows what a field is. But President Bill Gaede doesn't know what a field is. Interesting.
Fleming's rule, and it says, an electron circles, but it doesn't circle in the same place, along a plane. What it does, it moves forward as it circles, so it describes a spiral.
Like a tunnel.
Yeah, it's tunneling through, but it's going around. Now, why is this important? You would say, well, why would it do that? You have all these atoms lined up along that make up the cable, the wire, right? So you have all these iron, cobalt, whatever cable you've got, copper, right? And now this electron, the official version, right? We have this electron and it's going around like a spiraling. Why would it do that? When all these atoms are more or less aligned, why would it go under and over and under and over? You would think they would go straight, just like everybody illustrates them, just go straight from one atom to the other. Why would they circle? Why would they go around as they, and once again, let me give you a couple more just to make sure we get that covered. It's not that I pulled one out of nowhere and say, well, who knows? Here you see another picture. And again, all these pictures are from people who study electricity. And they say, look, the electron spirals along the cable, okay? The bottom one shows, the magnetic field coming, in this case, from the bottom upwards, the flow of magnetic.
Remember today, Bill said they never drew this stuff. But in this past video, he's shown pictures that experts in electricity drew to model how it worked. So I guess Bill disagrees with past Bill. President Bill says they didn't draw this stuff. Past Bill presents images of the models. So
the magnetic flux is going from bottom to top in that case. And you can see that there's the electron, the little red guy there, and he's going to go around a center. He's going to circle. And above you see it, how it describes its path along, the cable. Okay. So it's not that I'm inventing this stuff. I mean, here's one more just in case. Want to make sure nobody can challenge me on this. This is another one. You can see the spiral. These are all.
Well, I guess you're challenging yourself. Where was I?
All different websites, by the way, and you can see that again. It shows that within a magnetic field, the electron ball, the official version, is that it spirals. We have to explain spiraling. Okay. And just in case, I'm going to put the dynamic version here. And that's also based on Fleming's rule.
Bill, why can't we just define field at the electric field is the place electrons roam? The electric field is the place electrons travel on. I guess you say that's a concept.
And I'm sorry I blotted my face out, but there was no way of making this small for you to see exactly what's happening there. You can see the electrons are spiraling, okay? And they go in this twisted manner. They don't go straight. They spiral around the wire, okay? So
you know what? Wouldn't a football field or the horse field be a concept by the same metric? If we say that's the horse field's the place where the horses roam, the football field's the place we play football. Yes, those are concepts too, even though we could point to them. Well, we could point to all three. This concept object distinction just I'm not sure it holds under scrutiny.
Keep that in mind when we're talking about electricity. Electricity spirals within a cable. It doesn't go straight. Okay, and that's going to be important as we're going to see. It spirals. And just in case, we've got another one here, and this is in a beam line. This is in the cyclotron. And again, you can see, I don't know if you can see that very well, but I tried to do my best to highlight it. Here you have one electron. This is their official version. And you can see that it's spiraling along this twisted cable there, which is really its path. And its path is made of all these atoms. So the electron is just spiraling around them. Okay.
So essentially what you're saying is, if I get this right, every time I turn on the light or anytime I have an appliance that's using electricity, you have all these beads spiraling around the wires.
Yeah, and this is important because, we have to, I mean, if it goes straight, everybody says, okay, there's almost nothing to explain. It just jumps from one atom to the next, went down the road. But when it starts spiraling, you start asking, well, why is it spiraling? Is it that the atom is spiraling also? Is it turning around itself? Is it the spinning? Is that why? We have to answer this question. Okay, so let me get this guy out of there. Come back into square one here. And here's how they illustrate. Okay, I've done this little drawing, but it's based on what you'll see throughout the internet.
So in the past, Bill said this is how a battery worked, but today he said he didn't know. Amazing. He come on just fine in this video, but today he said, no one knows. This is absurd. Maybe he forgot.
And what you'll see is that this is a battery, okay? And on the right side, you have a lead plate. And on the left-hand side, you have lead dioxide, okay? PbO2 there.
So they're both lead?
They're both lead, but one is an oxide. One is made out of the oxide of lead. In fact, you see the colors are different. Those are essentially the colors that these elements have in real life.
And we have I guess we had the we don't have it negative and positive in the compound in the atom, but in this compound we have it defined. We have well defined. And that's very well defined. We could point to it. We could see all the objects.
Life. Lead dioxide is brownish, reddish brown, and lead is bluish white to gray. Okay, so they have two different colors. One is just an oxidation of the other. In between, in this, we have a soup in there. We have a liquid, and that's going to be sulfuric acid. And we're going to put it in with water. Okay, and so we have these two plates in this bath. And you can see that according to the official version, what we have is that the electrons, those red little dots that you see moving there, they're moving essentially in a straight line. And this is a little misleading. And this is probably the correct version, at least if we follow Fleming's rule. And that's that I try to do this as best as possible. Maybe you don't see it well, but if you check there, you'll see that they're kind of spiraling around the wire. Okay, that connects the positive to the negative end. So the electrons are really spiraling around. They're going like a torsion along that whole tunnel. Okay. So even if we're talking about electrons, and here we're talking about the particles like the official version is, we have to think of them as going in circles as they move forward. And if you look at that, that's a description of a spiral. Okay. So what do we have? Well, we have here an explanation of how some of this is done. Here is the, let me bring that first one back. I gotta say something here first. How is this explained? This is explained, in other words, the functioning of a battery. The battery is explained in such a way that the sulfuric that's in there it's going to react with the lead on the right hand side. Okay, it's going to react with the lead, and it's going to give us 2 extra electrons. Okay, so somehow, somewhere, for some reason that we still don't know, the sulfuric reacts with the lead, and because of this, the lead, which is very porous to allow the sulfuric to penetrate every little nook and cranny in there, ends up with 2 electrons, extra electrons. Okay, and as long as you don't put a connection there, it's going to stay there. It's going to store those 2 electrons. On the other side, on the brown side, where you see the lead dioxide, the same chemical, the same bath, is going to react with that lead dioxide, and it's going to allow it to have 4 positive charges. In other words, it's going to the lead on that side is going to lose 4 electrons. So this guy over here, the one on the right, is going to gain 2 electrons. The one on the left is going to lose 4 electrons. That is how you create the negative pole and the positive pole. It's a chemical reaction discovered by Mr. Volta in the 17th century. And essentially what they discovered is that this is a chemical reaction that stores motion, stores energy, ready to release it as soon as you put that green connection from one pole to the other. Okay, that's in general terms what we're going to be doing here. What we have to explain. We're saying here we have, one more time, we have the lead on the right hand side and the lead dioxide on the left hand side. We put these plates in a bath. That same bath reacts differently with the lead than it does with the lead dioxide. In one case, it stores or creates, generates, and then stores the negative charges, which is on the right-hand side there. And on the other side, it's going to store positive charges. In other words, what it means really when we say it stores positive charges, what we're saying is that it's going to need electrons because it's got holes. It's ionized positively.
So we're essentially, when we say storing negatives or storing positives, we're really just saying we're giving potential, essentially.
Yeah.
About potential. What, like, this thing now has the property that if X, Y, and Z happens to it, it will react thusly.
Yeah, essentially, this is more a description, not an explanation of why or how it does it. Right now, we're just doing a description. We're saying, for some reason, the left-hand side reacts differently than the right-hand side. And the left-hand side, we'll call that positive because we like the plus sign. And we'll say, look, on this side, it's going to store positive charges, and what we mean by that is that it's going to want electron balls, which for some reason are negative. And the other guy picks up 2 electrons, and he wants to release them. He's got too many electrons. And so as long as we remove that green connector between them, nothing happens. They just keep that charge in them because it's a chemical reaction with the yellow soup there. Once you put the cable to connect the negative to the positive pole, now the electrons start flowing. The electron balls come out of the lead plate and try to get into the lead dioxide plate. And of course, if you put a light or anything that you put in between there, it's gonna the electrons are going to go through that system that you put into that device or whatever. And it's going to light it up or make it work or whatever. It's going to cause work. And so this is essentially what we have to explain, okay? And what we're going to try to do is to explain it with the rope hypothesis. And I'm not going to do that today, by the way. I'm going to be doing that tomorrow because I need for people to think a little bit about these things. And
it's homework.
Yeah, it's homework, at least for the time being.
Okay. Yeah. I guess we can go into the explanation. He has it in his book. Let me let me bring it up in this book. Then we can end it for today. So 28, electricity and rope hypothesis by Bill Gaede. So the rope hypothesis emphasizes that electrons are not discrete orbiting beads. The electron is a balloon that encapsulates the proton. This assumption results in a different mechanism for how electricity works. When the distance between two hydrogen atoms shortens, the EM rope that connects them is gradually reeled into the atom, which what happens next if the atoms spin in the same direction, say CW, their electron shells blend to form the familiar figure 8 shape of the hydrogen gas H2. So imagine how a series of merged electron membranes. We refer to this as a serpentine. The rope model proposes that electricity consists of the spinning of this serpentine. Electricity can be likened to a drill bit trailing in place. Electric current doesn't flow, electricity spins. So, traditional version of electricity is a bunch of bullets, and the proposed version is a drill spinning in place. And here's another picture. Traditional current, flow electron beams, creating a circuit, and in the rope hypothesis, it's a spinning serpentine, like a drill, which kind of makes sense actually, because you spin to generate electricity, and that's kind of how it gets here anyway. So to do voltage, yeah, we definitely should do voltage. We're back to that battery. So voltage, 29 voltage. The typical analogy to use to explain voltage consists of two water tanks at different altitudes. The point of the analogy is to show that there's a difference in potential between the upper and lower tank. Water flowing downwards through an interconnecting pipe simulates the flow of electron beads. The first practical batteries had lead terminals immersed in sulfuric acid, we call sulfuric peroxide. H2SO4 bath, the lead reacts with the sulfuric peroxide and negatively charged electrons begin flowing to the positive terminal. Under the rope hypothesis, the chemical reaction compels the serpentines rows of merged atoms of one of the lead terminals to rotate. CW, this induces the serpentines comprising the whole wire connected to the terminal to also rotate clockwise. CW is clockwise along its entire length. A person looking at the wire at the other end will see the serpentine spin counterclockwise. Keep in mind that it is not the wire that is spinning, but the rows of atoms that comprise it. Voltage is not an abstract difference of potential involving pluses and minuses. Voltage is clockwise and counterclockwise spinning of a row of atoms or molecules. And this is a static version of the old model. The the accepted model and the rote model of electricity working in a battery. So in the book, we don't have to wait for the next video, even though that's just a clipped video. That's just an edited down version of a video that was released a long time ago, which you already saw. But it's right here in his rote model book. I'll make sure there's a link to it. And I think this is the last section on electricity. 30, electricity in a vac, aka electricity in a vacuum. What would happen if we hold current and voltage consistent between cathode and anode and continue to pump the vacuum chamber? Will current eventually stop flowing? So electron beads flow through perfect vacuum, reaching type of matter. Ooh, there's a bead being shot somehow. Or do we need matter to conduct electricity? Perfect vacuum except for several atoms. So if we remove atoms, a series of electron bullets would have less obstruction, and this should increase the current. Experience shows otherwise. Current stops flowing at some point. This suggests that electron beads cannot flow through a perfect vacuum under any voltage. Atoms must be present. A conductor is made of atoms and not of the absence of matter. Accordingly, the Rope hypothesis proves that electric current is not present unless atoms serve as mediators. The model suggests that electricity is mediated by a continuous string of merged atoms stretching from cathode to anode, which we call a serpentine. Thus, flow of current is a serpentine that twirls in place. Think of a string of balloons merged in tandem, surface to surface. You torque the first one and the entire line spirals in place like a helix. These are just more images, classic, and the serpentine again. Yeah, that's the end of the electricity portion. Oh, I should show. I need to go back and show the actual images. I forgot. I didn't. Let me go back. So yeah, 28 shows the serpentine merging. He didn't label the exact. He didn't label all the images. So this is bullets and a drill, and here's what's it called? How do I describe this? That is electricity bullet model versus electricity serpentine picture diagram. This is the batteries again. That's the one he presented his video, and this is the serpentine newer version. There's a couple. This is a vacuum diagram. The electric bead versus the beads, pretty much a wire. Another, that's the wire again. And I think we saw these diagrams before. And that's the end of electricity. Yeah, that's probably just gonna be edited down to like 15 minutes. Yeah, I think everything I covered, that born part about be edited down to like a 20-minute video. Now, this is a good part. This is good a place as any to end the stream. I'll make sure I'll link to the book inside the description if I didn't do it already. See you later.